we still have the will to do the editing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 left to do. And we saw the data quality. I think this project we have many extreme washout. Yeah, it's hard to handle.
Okay.
And that's it.
All right. Well, if I get some time, I'll jump in there too and try to help. If you can dump this spreadsheet in the
Okay.
Papata chat
Okay.
so that I can see it.
Yep.
We need to wrap up the Daniel thing too, and then Harper's probably going to have some more stuff for us here coming. And then I haven't heard anything yet back from Eric. He asked the question about the pricing. I responded to him, and now they're probably discussing that internally what they want to do in terms of budget. They want to do 7 wells. They want to do 30 wells, right? Because it's going to cost more money to do more wells. So we hear back from them, we'll worry about that at that point. So
then for the frying adjustment, we need to do about editing, right?
Just at this point, yeah, just through the editing stage, right, and normalization. And then we'll kind of shelf it and then come back to it and finish the interpretations or whatever later.
Okay,
but
good.
it's up to you. I mean, like you know as well as I do now that if you do the analysis, it takes 3 hours or whatever, 2 hours are spent depth shifting and editing and normalizing, and the last 15 minutes is spent doing the actual interpretation. So if you get all the way to the end, you might as well just spend the extra 15 minutes to finish it. But the critical piece is really coming back and looking at the data set as a whole, right? Making maps and understanding, using these pieces of software like we've been using to understand, well, why is the Dean in this one well so much different or something, right? Like, why does it look different? And then usually there's always a story behind that. The reason it's different is because there was a big washout. And even though we used our best machine learning to correct it, we were still wrong. Like there was some additional normalization that needed to take place, or better editing or multi-well editing or something to get that sorted. So that's what takes a lot of time. And that's the most crucial piece. For this seismic survey inversion work that's being done, the critical thing is well ties at this point for a low frequency model. And for that to work, we have to have basically the spikes and washouts removed from the density and sonic data. So Jorge is very picky, but he also likes the data that we've been giving him, right? He really likes PetroRes logs. They look a lot better than anything else that he's seen, right? Because we spend so much time doing it the right way. So, that's what we need to do here. At some point when we get past the low frequency model and they start looking at more stuff, we're going to want to have the rest of that. And also we want to just deliver that to the client anyways, right? A full interpretation for them. Like maybe a geologist is going to be looking at that area too, or something. What else is going on over the weekend?
So are you ready to go into the next step? Yeah, are you good with the depth shift?
Yeah.
Tell Ryan to how many hours?
Yeah, well, so what, right? Like I've probably spent 5 years of my life depth shifting. It gets worse, trust me. But it's good that you understand the problem also, because like I had mentioned before, you know, uh, I would like to find a way to automate that process and have the computer do a lot of it for us. So just think about that, right? But yeah, take him through the whole workflow from start to finish, the inversion, everything, right? And kind of QCing data.
Yep.
Yeah, you can do that with just a couple of these wells from the Flying Dutchman. You don't have to do all of them, but just take a few of them that are the highest quality or something and run them all the way through. And hopefully you'll see stuff when you do that, right? Like one well's got a bunch of dolomite in it, right? Because there's a problem with the
Oh,
PE or the neutron or something, and you got to fix it and so forth and so on.
okay.
And the other thing too is if you can, like Game had mentioned to me, Best is had put together a calendar for 2025, but she never did for 2026. So I guess Gabe's done that now. So if you can get with her and then retroactively fill that in or whatever, and if you plan to take vacation, let us know and keep that up to date, right? I don't know how she's planning on doing that, if it's going to be a spreadsheet or whatever, but I know we've got some holidays coming up here over the next couple of weeks too, so just fill it out, do what you're going to do. Yeah, other than that, I guess if you can do that output thing for Harper, right, for what she asked for. So she wants that missing data. So all the lithology stuff from mineral solver, quartz limes, clay, TOC, all that stuff. And I will look at, well, let's just do that tomorrow. Well, I'll put that for her now, and then tomorrow during our meeting that we've got in the evening, between now and then, I will try to get that RW data, and we can look at the interpretations, because I think we ran the probabilistic saturations program on all of those thunder wells, right? So we'll make a map of the RW P50 or whatever it is in there. And we'll look at the values that came from this water catalog that I found earlier today from QEP. And we'll see.
She missed the spreadsheet that I made.
I don't
Right.
know, just email her, I guess, and see or you can send her a message on Teams. You know that, right?
Okay. I will resend it on Team.
Well, you may
But
not be able
output.
to. You may not be able to send files on Teams because it's a different organization, right? But you can send her a message
Oh,
on Teams. You just put her email address in there. You can start a chat with her. But yeah, just get with her and figure out, you know, I sounded to me like she wanted last files, right? Not just the spread
okay. Okay.
with all the mineral solver outputs and stuff. What I would do, just to cover all the bases, is I would export the last files with the mineral solver mineralogy curves and BTOC and clay and all that. And I would also do the statistics over the pen, because it takes you 5 minutes, right? Once you got it open,
Yep.
just run the multi-well curve statistics as well, and then just give all of that to her. The last files we may need to upload somewhere onto the Diamondback server, in which case I'll need to do that probably. So what you do is just put them somewhere on OneDrive where I can get to them, and then I'll go in and upload them to the Diamondback server for her to
Okay.
find.
Good.
But yeah, tomorrow what we'll do is we'll look at the RW values from this new catalog, and we'll see what we were using and see how different they are. And we can also dump that into the new software and export using that program or whatever, export Thunder to the new software, and then play with some of the RW stuff in there as well. But I don't know that that's going to be a big deal as much. Like I think those values are fairly very close.
Mhm.
But if you caught on, what she's talking about is, we need to figure out one of the reasons that. So what's happened is, let me back up. What's happened is this project came out like last November or whatever it is that we were working on it, right? And nobody really kind of gave a shit about it. They were interested in other things. Then this whole Barnett thing blew up. And, the company's leadership said we need to start looking at all these other things. The Pennsylvania shale in New Mexico came back again. And now they're throwing resources at it. So Harper's got a team. There's people looking at it now. Now they're interested, right? It sat for like 2 or 3 months and now it's hot. And the problem that we've got that we're trying to reconcile is that the wells themselves, they're deep, they're organic shales, and they're fairly well pressured, is what she was saying. And when we go to do saturation work, which you can go back to that Thunder project and check those saturation curves, like the P50 water saturations, they're fairly high, right? Like 30, 40%, 50%, whatever. They're fairly high, which is a problem because the wells are not producing water, right? So the question is, what the fuck's going on? Like, why is the water not coming out? Is it because our saturation equation is wrong, or is it because there's some other mechanism, where we've got a water wet system, oil flows preferentially through pores, a lot of the water is bound water. Something weird is going on, capillary crap. There's some weird relative permeability shit going on. We don't know, right? And what she mentioned is, in Archie's equation, if we go in and change the M cementation exponent to like 1.5, it'll reduce the water saturations that we compute a lot, right? And we don't really have anything that we know that we got this variable MN model. I think it runs from like 1.8 to 2.3 or something. And we don't have a lot to go on, but we could have sandstones or silts or something in there that's got that sort of cementation exponent going for it. The other thing that will change, so let me do this real quick. The other thing that'll change Archie's water saturation is the N exponent. So, if you look at a Pickett plot, you got porosity, total porosity, and you got resistivity, right? Something like that. And so, you got some data cloud. There's your data cloud, right? And so when we do the analysis on this, we draw a line where we think this is what the wet formation is, right? So saturation line here is 100% water saturation. The slope of this line is M, okay? And that is the cementation exponent that's responsible for like the fabric of the rock, right? And how the saturation changes with porosity, basically, right? Because the steeper the slope, the bigger the derivative, right? The more change happens versus resistivity. So that's how that comes into play. Where we move this line changes the RW value, right? But the RW is actually like, what is it? SW to the N, right, is equal to ARW PT to the M RT. I believe that is correct. Right? That's Archie's equation for total porosity. So normally what they do, they put a 1 over N over here or something. And then fuck with my erasing. They erase that, right? Now, you can, the reason I wrote it that way is I want to put this back over there. You put that back over there. And then you multiply that by PT to the M times RT divided by A. That's equal to RW, right? Following me? So this is our saturation line. We got all the M is part of this equation, is what I'm telling you. If you look at RW, it relies on M. A we don't really care about because it's usually equal to 1, you know.
Yes.
So formation factor, all that stuff, we don't really give a shit about it. So it, you know, actually RW is based off of MN, porosity, everything, right?
Mm-hmm.
What you solve for it, but really it has to do with where that line is and what the slope of it is. Now, what a lot of people don't understand is this thing. The fuck is that? What is N? Physically, what is it? Like when you think about you know, pore system and rocks or whatever, you got all these pores that are kind of like, you know, they're in there hanging out, right?
Yep.
Little happy pore there, sad pore, right? Archie's equation is dealing with coupling, really, resistivity or conductivity, whichever way you want to look at it, is somehow proportional. Okay. And this is the resistivity of the water and the resistivity of the formation. All right. Again, if you work this out, I can leave this over here, right? I can put RT over here, get rid of it there. So my resistivity ratio, more or less, is proportional to the saturation, right? Resistivity ratio of the water to the formation reading or whatever. Yeah, it's sort of that simple, right? So this cementation exponent, like, you know, how does this thing come into play? What does it affect? What is the physical process for it, right? And what is this thing? What is the saturation exponent? So the math itself, the way that it works, if you do the differential equations and all that shit, right? Partial differential equations, and you try to break, you know, you leave one variable and then you change the other one, do the derivative on the other one. So it'd be like a d m or whatever, right? All that kind of shit. What you're going to get is something that looks like this. You get a gradient. 3D calculus 101, right? You get a gradient, and this gradient goes from 0 to 100, just like that. So if you set your N incorrectly, right, I could have data over here that actually has saturations that don't make sense. You know, same thing if I set my M curve, I have saturations here that are negative. They're below 0 because this is the 0 line, right? Or I'm sorry, this is the 100 line. That's completely wet. So these are greater than 100% water saturation, right? Got that backwards. I was still thinking I was over here on this end of things. So, you know, the whole point of kind of using Archie's is that over here, I'm trying to move it, and won't let me move it. Is that you know, you set this thing up, so you got this line set with that gradient, right, going that direction there. And the idea is that the data set that you've got matches that. So this is the wet stuff here. And usually it's like the highest porosity wet stuff that we want to match that to also, right? Is we don't want to match it to noise, right? Data points that are all over because the porosity calculation is wrong or something. We want to get a nice big blob of data here. We say, okay, that's the wet line. Now, this slope, right? How do we set that? It all depends on what the data is. Data could look like this. Well, this is interpretive. Is that the slope? Is that the slope? Like, I don't know. Could be anything. But that changes the saturations that we compute because it changes the M. Right? So, what you'll see in that new program too, I kind of tried to automate some of this stuff. Like the data from Harper's world is going to look like that or whatever.
Yep.
And we may be able to fit a curve through it that looks like this, that looks like this, right? Maybe this is a 1.5, that's a 2, something like that, right? Or actually, it'd be backwards, I think. That'd be a 2, that'd be a 1.5, whatever. These two states, yeah.
This is the Archie equation. So what about Archie phi t that we also usually use in the IP?
That's what
Is
this
it the
is.
same?
You just put VP here, yeah.
Oh, okay.
Archie effective, would you put effective porosity here?
Oh,
So this includes clay-bound water, right? This does not.
mm,
But what you wind up with is if you've got a saturation curve that kind of looks like this, right? Where this is 100% near, and that's 0. If you put a smaller M in, you're going to get a curve that's got something that looks like that. Right? So it lowers the saturations by putting in the lower M. Okay. And that makes sense if you think about it, because if you've got this sort of data here, like I've shown, right, where you have this this blob, if I draw a line through that like this, then that's all high saturation stuff. Even if I draw the line down here to match, okay. This now, all this data is further away from the line. So it's lower saturation, right? If I draw the line like this, everything is closer to the 100% line. So it's higher saturation. And then as you take this second variable, it's like it's an accordion, right? If it all collapses really quickly, that gradient, then my saturation exponent has a very high gradient value. Then as my resistivity increases, right, my saturation decreases rapidly. So I could have 0% water or 0% water saturation, 100% oil right there if that's where my gradient headed for that saturation exponent, right? If my saturation exponent looks like this, goes way the hell out here, really far, right? And all my data is right here, then it doesn't make a difference what I do with M and N and the wet line or anything. I'm still always going to have like 80% water saturation because N is forcing it. N is the gradient. So does that make sense? Trying to, there we go. Move it again. I don't know why sometimes it works, sometimes it don't. Okay, just one button, never mind. But it all comes back to this equation here. So if you wanna understand this some more, you can try to figure it out, like solve for each one of these things. And try to differentiate other shit away, right? If you hold one of these constant, right, and you do a partial differential, partial derivative, it's a constant value, so that goes to 0. But yeah, you can just see just from this sort of equation that SW, you want to see how that is a function of what? Say M, right? You want to do M. So you got to divide by RW, right? And then multiply by RT. That is equal to TT to the M. So now you got to get into like logs and exponentials or whatever power functions, unpowering things to get this out of here. So you could take 1 to the M power if you want to, blah, 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 work it out, figure it out. Take a log base M or whatever to get, or log base, I don't know. I have to look at the math again, get rid of the PT and put the PT over here. But this is what's happening. So anyways, my comment that I made earlier is, you know, how much this RW change we make is sort of impacting the overall saturation computation versus this M. This is going to be a bigger driver. So Harper's right? We put a 1.5 in there, maybe a 1.8, a lower value than they're normally putting, and it drives that saturation down lower. Looks something like that instead. You know, where well, you can do that. I'm trying to be neat here, but it's difficult. There's 0%, let's say, right? This helps explain, because like right now we're up here. That helps explain why the water production is so low, because maybe this is the cutoff, right? We understand this reservoir a little bit better. This cutoff might be like 20%, you know? And if you come over to an organic shale and you look at a set of relative permeability curves, right? So let's just say that's K water, right? And this is K hydrocarbon or whatever. Right, you have this irreducible saturation and stuff where the relative permeability is essentially 0, right? And then there's a point where, let me make this easier to look at. So I'm going to lose you otherwise. Like it's flat, right? Like the water rel perm, this is 0, that's 1. Okay, water rel perm is flat, and it's like 0. Water is not going to move. It's stuck. And this is saturation here, right? So water saturation increasing that direction. At some point, it just starts, oh, stupid ass thing. At some point, it just starts to move. And it reaches its maximum at 1, right? So what this is telling us, it's a relative permeability. It's a fraction of the absolute permeability and the capacity of the rock to provide. But like right here, undo that. Right here in that zone, up until here, it's 0. So say this is 50%, right? 50% water saturation. You have to have more than 50% water saturation, otherwise water doesn't move, period. Right? So, you know, back to Harper's question, is that if this is less than 50%, say it's 40, but this is 60 over here, right? This one's 60, that one's 40. By changing the M, that's the difference between water moving and water not moving. It's the difference between producing water or not producing water. Right? Make sense? Questions, comments, concerns? 8.
Alex. Alex or aliens. Good, good.
Okay, I'm not losing you on this relative permeability thing. You got that?
Yeah, I got.
Okay. All right, so we'll connect tomorrow, I guess, talk about the RW values, and once I get that data, and we'll look
Good.
and see what's happening here with this other part of
Yeah.
the equation, right? And what the M's and N's are or whatnot, and we can zoom out on this.
Yes. Okay, thank you, Ran.
Yeah, that's what I'll
Take
just next
care.
time I'll just zoom in and out. It's easier and you can.
Zoom in and zoom out.
Okay. See ya.